Here we go. Boolean connectives. The basic idea here is that we started off with atomic sentences, and if you remember the image I gave at the very beginning in the lecture and also in the video lecture was this notion of our universe. This is a classical picture of how the universe works. It no longer holds for modern physics, but it's still pretty accurate. In the classical view of the universe is composed of atoms. Atoms are unbreakable components. They can't be reduced down anymore, right? And for us, the atoms are things like what you find in your periodic table. You put them together to form molecules. Molecules get put together to form bigger molecules, macromolecules, and then so on and so forth, and it gives you everything in the known pattern universe. Wind, air, fire, you and me, planets, the universe, everything is composed of atoms in motion. Okay, so Boolean connectives, how that links up to that idea. Boolean connectives are the glue that put together atomic sentences, not atoms, but atomic sentences, which are basic units of meaning, into larger units to form what are called molecular sentences. The connectives that we're going to study to start off, there's three of them. One Boolean connective is not, another one is and another is or. They're called Boolean connectives. They're called connectives because they join up with atomic sentences to form bigger things. And they're called Boolean because of the person who came up with this. His name is Boole. He was a mathematician, philosopher, logician. He did a number of things. He's an interesting person. And he was trying to figure out, are there things like laws of thinking? Now, there are sort of laws of physics, laws of biology, laws of chemistry. There are regularities in the world that describe how things behave, right? Like law of gravity means you drop two objects, there's a certain regularity in which that occurs, and you can mathematically describe that regularity. There's laws in physics, laws in chemistry, laws all over the place, okay? Natural laws. Boole was wondering, are there such kinds of laws for thinking? And he said, and this is not totally accurate, but good enough for the sake of the lecture. He says, look at various languages. If you extract common features across languages, because people's thinking occurs in language. It's not just in their heads, but what they write down and what they say. So insofar as you can study thinking to see if there's any laws, look at the way in which people write across languages, in German, French, Japanese, Chinese, English, you name it. They all have these kinds of connectives. Something like not in English would be nicht in German, and you got all these kinds of same operators, connectives, in all languages. And, or, and in Spanish would be e, and so on and so forth, right? So we're starting off with three, not and or. And they, again, the logic of this is they get put together with atomic sentences to form molecular sentences, basically bigger units of meaning. Why are we doing this? Keep in mind, what logic is studying is inferences, right? So if we can track the inferences by how they're not just put together in terms of their basic components, but how they flow from those basic components into larger units of argumentation or whatever it is, we'll get a better sense to capture those inferences without being enslaved to them. This requires that we, like mechanics of the mind, look into our mind and see how some of these thoughts are structured. And that's what Boolean connectives is getting at. Okay, so let's start off with not. Not right here is symbolized with this funny looking right bracket thing, right? It reads in English as not, and it's symbolized as not that sometimes called a, well, we'll just call it not. That symbol gets attached to an atomic sentence. So let's call S an atomic sentence, and it reads, it is snowing. A simple idea, right? So it is not snowing gets symbolized as not S. Easy, right? Okay, let's continue on. The other two connectives, and or. The and is the upside down. It's this. It looks like an arrow pointing up, and the or is a V-looking thing. You can think there's actually a symbolic reason why they're formed this way. Maybe later in the course I'll get to this, but for right now we don't need that. Just remember that symbol is a symbol for and that other one is a symbol for or. So if I say it is snowing and it is raining, that gets broken down into two component parts, atomic parts. It is snowing is one component part. The other component part is it is raining. Let's symbolize the first one as S for it is snowing, R for it is raining. And then the and gets rendered as that symbol. So translating it is snowing and it is raining in English into our language is symbolized as S that funny symbol R, S and R, yeah? Okay, now we have what's called a truth table. A truth table we're going to cover later in the course in greater detail. Here's your first pass at this notion. Um, a truth table is this thing right here. You see how you got that cross right there? That's the truth table, and it basically gets at the breakdown of a sentence, whatever it might be. So let's just look right here at this first truth table. The truth table for not, which gets at the logic of not, says on the left side you have some component atomic sentence. I have here P. P is any sentence whatsoever. Let's use S for it's snowing, right? In our logic, we assume everything's true or false. It's a very rigid system in that sense, but remember, this is the simplest of systems. Everything's true or false. Obviously, in the world, there's shades of gray. Not everything is true or false. Most things are, sort of true, partially false, and other combinations. There's actually higher level logics that deal with this, and one has direct application in your everyday lives. There's something called fuzzy logic that deals with sort of half something that's sort of true and not really, and it has to do with learning mechanisms. Like a good example of this is the brakes in computerized cars. If you got an advanced system where if you hit the brake, you go skidding and it causes an accident, and you don't want that, smart brakes learn from the way in which a driver drives, adapts to their driving tendencies, and so if they hit on the brakes and that'll cause the car to skid out of control and tumble over, it actually reduces that and brings it down to a more gentle brake, but not getting into an accident with whatever's in front of the driver. That kind of logic governing how that works is called fuzzy logic. It builds upon our basic logic, but remember, that's higher order stuff, very practical, but beyond this course. We got a simple system. Our simple system says we only got two choices. Everything is either true or false. Propositions, statements are either true or false, just to make it easy, right? So S for here, the first one, instead of P, let's use S for it's snowing. It's either true or it's false. It's either snowing or it's not, right? So the statement on the right side, not S, says it is not snowing. What's the logic of that? Well, going over to the left side, if it's true that it is snowing, then the statement, not S, it is not snowing, is false, right? And likewise, if it's false that it is snowing, so the statement on the left side, P, in this case S, right, is false that it's snowing, then that means the statement, not S, it is not snowing, is true. So not, if you think about it, all it does is it flips around the value, like a light switch. If you have the light switch on and you say not to it, it turns it off. If you say not to off, then it turns it on. Not just flips around the truth value, whatever it applies to, okay? And is the next connective, and here's the truth table for and. There are more combinations here. If I have two sentences P and Q, turns out there's 4 total possibilities. There's a formula for this. It's 2 to the number of pieces, 2 to the power of the number of pieces, exponentials. This is about the only math you're going to get in this course. And the basic idea behind it is that, and I'll explain this later as to how it works, but let me give you a quick rundown right now. It's 2 squared, so that's 4, 2 times 2. You always start on the right side and you alternate true, false, 4 times, because there's only 4 combinations. And then you go to the move over 1 and you double what you just did. So if this is 1, 1, 1, you alternate, then double 1 is 2. So true, true, false, false. And this is a mechanical way of getting at all possible combinations. How do you know they're all possible combinations? Well, think of these as 2 bets. You have a bet on Philadelphia and a bet on, I don't know, I'm going to make it up, Quebec. Quebec doesn't have a team, but whatever, right? 2 teams you're betting on. There's only, and forget ties and all the rest. Remember, there's only true or false, win or lose, right? Nothing else in between. You can either win the first, lose the second, lose the first, win the second, or lose. Think about it, no other possible combinations. So what a truth table is getting at is an exhaustive list of all possible states of affairs, things that can happen, okay? And then relative to the things that can happen, you then want to evaluate the truth of the statement. So let's make this easy. Suppose P and Q are, P is I'm going to the game, Q is I'll eat a hot dog, or let's make it better, I'll have a beer, right? So P and Q, I'm going to the game and I'm having a beer. When is that statement true? Well, let's break it down on the left side. If it's true that I went to the game and true that I had a beer, is the statement I went to the game and had a beer true? Yes. What if I went to the game, true, but the right side is false, I didn't have a beer? Is it true that I went to the game and had a beer? No, so it's false. And likewise, if I didn't go to the game but I had a beer, the statement I go to the game and had a beer is false, and false in the last case as well. So this is the logic of and, if you think about it, anytime we use it in English and for that matter any other language. When you're saying you're doing this and that, and by its natural logic, remember logic is reflecting upon our own pre-theoretic practices which we don't often think about. And is true whenever all the components are true. So the best way to remember the truth table for and is it's only true when both sides are true. If someone tells you, makes you a promise, I'll get you dinner and I'll buy you flowers. Say you're going on a date with your girlfriend or the reverse, whatever it is, right? That's only true when both components are true. You go out for dinner and you get the flowers. Okay. Moving on. The truth table for or is slightly different. Or in our system is what's called inclusive or, not exclusive or. Exclusive or is the way in which or operates in a lot of situations in the real world. There are cases of inclusive or as well. If you say like, okay, so let me give you an example of the first and then I'll give you an example of the second. So exclusive or, you go to the restaurant, right? And you order some plate lunch, whatever it is, chicken cutlet. And then, or if you're vegetarian, your tofu cutlet. What does it matter? That's whatever, right? And then you're given options. Let's suppose you're only given two. You can get fries or rice with that. The or here is exclusive in the sense that when they say you can have fries or rice with that, you have to choose one or the other, but you can't have both. That's implicit in the or, the option that you're given, right? It's one or the other, excluding both. Inclusive or, by contrast, says you can have one or the other or both. If someone, for instance, gives you options, what do you want to eat for lunch? You're going out somewhere, and they say, you want plate lunch or pizza? And you go, yeah, whatever. That means you could get plate lunch, you could get pizza, you could get both, whatever. So that's inclusive. Exclusive means one or the other, not both. Inclusive is one or the other, and maybe both, right? And our logic system says we're going to use inclusive or. So or is true when you have at least one of the sides true. So let's look at that for the truth table. P or Q, when is that true? If you have both sides true, that's like getting pizza and getting a plate lunch. It's true. That's like the bonus, right? You get pizza or you get a plate lunch or both. That's fine. True, false makes it true. False, true makes it true. The only case in which it's false is when both sides are false. The options, that is to say, you get, so let's go back to the restaurant analogy. If the waiter or waitress comes up and says, okay, you can get fries or rice with that. The only case in which they're not telling the truth, in which their options that they laid out is a false option, is when both sides are false. So you say, look, they ask you want fries or rice with that? You say, I like fries. And they go, no. What do you mean no? You gave me the option. No, you cannot have, we're all out. Okay, I'll have rice then. No. What do you mean no? You gave me an option. Oh, we're all out of that too. That means the option that they initially gave, fries or rice, is false. Yeah? So you can remember the truth table for or as in one of two ways. Either one, at least one of the sides is true, or conversely, it's only false with both sides false. Here's the takeaway, what you need to memorize for the truth table. If P is true, then not P is false. Not just flips the value. Whatever it applies to makes it the opposite. And is only true when both sides are true. That means if any side is false, the whole and sentence is false. And lastly, or is true when at least one of the sides is true. Conversely, it's only false when both sides are false. This is how you memorize the truth table, because you're going to apply it over and over again, so it's worth memorizing these things. Alright, before we move on to the homework, if you want an application of Boolean connectives, I mean, a lot of questions that get raised in logic, there's a lot of questions that people have, but one that often occurs is, how does this matter at all? How is it practical? That's a question that has many answers. Practical in what sense? Here's one important one. It's hugely practical. How? Well, the basis for all your electronic devices, for computers, for your cell phones, for credit card transactions, for the web, all of this is based in computation, and computation is made possible by this Boolean logic. I don't mean that figuratively, I mean that quite literally. If you open up any computer, what's in it at its base level are these circuits, and the circuits run on these things called boolean connectives. That's part of what they mean by the digital revolution. Another example of this is TVs. If you remember back in the day, old TVs had rabbit ears, and the signals weren't very good. And then later they have digital TVs, and you look at it, and the picture's great, the resolution's great, and what marks the transition between the what are called analog TVs and digital TVs is basically a Boolean type logic. What do computers run on at the root level? Basically zeros and ones. It's a sequence of zeros and ones processed really fast, off and on, basically, true, false. That's what's meant by Boolean. It's only one of two states. It processes these things really fast, these 0-1 combinations, and then it patterns them up with these things called algorithms, which we've covered briefly before in one of my previous lectures. And these algorithms then pattern up the zeros and ones in greater patterns and basically give you everything that you experience when you interact with the computer on your personal computer, when you talk on your cell phone and that thing sends a communication as a text or however else you're communicating with another party, or you're doing some search on the web. All of these things are basically in the background 0-1 flows of information. If that's not practical, I don't know what it is, because it has fundamentally transfigured our modern kind of society, which is very much a digital culture. Yeah. So if you want something that's hugely practical, there it is right there. Boole is already run amok in the world every day. In fact, all these zero ones are floating through space right now in various signals when you use your cell phones and whatnot. It's not just literally in your computer. It's all over the damn place. One quick example of this, if you don't quite get that, if any of you seen the movie The Matrix, it's chock full of philosophy, but here's one example of how this digital flow works. So if you remember, for those who saw it, if you didn't, go check it out, it's worth seeing. You remember there's this flow of information coming down, and then what happens when they zoom in on any one part of this flow? You basically get the whole matrix, right? But behind the scenes, behind the matrix, that's what these pictures are about right there. It's basically a flow of information. When they zoom in on the thing, then you enter into the matrix. So the idea is the manifest world of what we see, and touch and feel and hear and smell, that's taken for granted. But if you go behind the scenes of that manifold image, that movie image, go behind the scenes of how the movie image is made, it is this flow of information, and that's basically getting at this Boolean kind of world that we live in. It's zeros and ones flowing all over the place, creating the patterns that we think are real, when in fact, at root, they're just zeros and ones in really complex kinds of patterns. Okay, so that's it for Boole. Now let's get to the nitty-gritty. For homework 4, 3.3, you can try that. Look at my lecture in La Lima, read it through. It's got, besides the audio file and the picture files, it's got a video link taking you through how to do 3.3. For this lecture, I'll really quickly take you through parts of 3.6, and then I'll let you guys do the rest. 3.7, I have that in the audio file. I also have a picture file of the answer in case you get stuck, but it's worth that the time for you to spend listening to the audio file and thinking through how that works. 3.9 is just like 3.6, so that's why I'm just going to do 3.6, and if you get that, you can try 3.9 on your own. And then 3.10, I also give you guidance there, and if you get stuck, I have a picture file giving you the answer just in case. Remember, working through this stuff is what matters most, not just getting the answer. It's how you get there, not the answer itself that matters. But the answer does matter in a minimal sense. It's giving you the points you need to pass the course. You've got to get the 2 points on the homeworks. That's the crucial thing, which links back to why philosophy is sort of an exercise in discipline of the self. Logic as sort of self-reflective study of creating habits of the mind that will help you to organize your own thoughts as well as your own being. Okay, so 3.6 in the book, here it is. It says, first, copy in the sentences that you see here. Make sure you copy in them exactly as they are. There are 10 total. Be especially careful of the parentheses. The parentheses are very, very important, and I'll talk about that next time. But for right now, make sure you copy them exactly. When you turn it into the grade grinder to yourself, if it says it's wrong, go back and make corrections. You're probably missing a parenthesis somewhere. So to start you off, to show you what I mean, this first one, right? F is tet F and small f. So enter that in, tet F and small f, which reads in English, f is a tet and f is small. Okay, that's good. And you keep copying them in. I'm going to add in at number 7, this one right here, what's in there. Some of you will write the following, not parentheses, watch that, tet, f, and small f, and you'll stop it there and think that's it. But you notice at the very end there's another parenthesis, right? That parenthesis matches with the first one. So if you notice in the Fitch program, there's this flashing feature. It's in green. If I click on the right side, it should flash with the other side. That's its matching partner. If I click for the tet f next to that, it matches with that. Those parentheses right there next to the tet, the dodec, the small, and etc., they don't matter. They're just going with that. They're just the matching parenthesis with the constant inside. It's the other parentheses that really matter because they group things together. So when they match like that, what the parentheses does is it essentially makes that whole chunk into one thought. And then the main connective, what's called the main connective, what's left over, what's outside of parentheses, is the thing that applies to the thought within. So for the first one, f is a tet and f is small, the main connective is and. It's the only connective, so it's the main connective. For the second one, 7, you have two connectives. You have the and the not. Which is the main connective? Well, the main connective is always outside of parentheses, or what I'm saying is left over, meaning what do I mean by left over? Well, suppose I chose and as the main connective. What does it join? On the left side, it joins tet f, and on the right side, small f. So if that were the main connective and, the problem is there's something left over, something not accounted for. It's the not. Since the not's not accounted for, that means the not is the main connective, not the and. So what the parentheses does is it effectively makes that statement into one thought. F is a tet and f is small. And the not on the outside is saying that whole thought is not true. Okay? That whole thought is not true. And if you think about it, that's in direct contradiction with what 1 says. 1 says f is a small tet. 7 says, that thought, f is a small tet, is not true. Yeah? This is different than if I had not tet f and small f. The only difference between these two is in the second one I left off the parentheses after the not and at the very end. At the very end. They look the same, but the parentheses are missing. This says something entirely different. This one says f is not a tet and f is small. The main connective here is the and. So you're saying f is not a tet. It's a cube or a dodec. And f is small. So it's definitely small. Whereas the first one says something different. It says it's not the case that f is a tet and f is small. So you're saying take the thought that f is a small tet. That's not true. F could be a tet, but it's not small. Or f could be small, but it's not tet. You just cannot have f being a small tet. Yeah? Whatever f is, it's not a small tet. That whole thought is being denied. So for 3.6, you're going to first copy in all the sentences. There's, did I say 12 in the beginning? Sorry. There's 10 total. Make sure you get all 10. You save that as sentences 3.6. The second part of this assignment is then relative to the world that you open up, which is Wittgenstein's world. You're going to mess with just f. I didn't open it here, but you guys can open it on your own. You're going to mess with f, and you're going to try to make the most of 1 through 10 true. You will not be able to make all of them true. The reason for that is some of these will be in direct contradiction. Like 1 and 7, you can't make them both true together. There's going to be other cases like this. So you're going through it, you mess with f in the world, hit verify, try to find the most number of truths you can. If you think you got it, turn it into the grade grinder. It'll basically tell you if you got it right, or if there's more other changes you could make that would make more sentences true. So you just keep playing with it until you find the right combination. Yeah, that's it, and that's for 3.6. Okay, for the other assignments, remember I have either video guidance or answers posted in La Lima in the lecture and in the picture files, and the audio file will guide you further. So that's it for this lecture. Make sure you visit those other materials because it'll help with the slow digestion that's needed for logic. Alright, see you next time.